Alright, in this video we're going to talk about Chapter 4, and this is where things start to get a little bit more exciting. So let's go ahead and jump into that. In Chapter 4, let me just actually back up a second and remind you that what we're doing here is we are trying to understand, and I'm talking about the big picture statistics, what we're trying to do is understand the population characteristics. So say we've got a population, it's got characteristics that are called parameters. Those are things like mu, sigma, pi, theta, etc. Characteristics of the population, if the populations of any interest to us, are things that are unknown and unknowable. And so we want to be able to estimate these things, because if we know what the characteristics of the population are, then we can make decisions better. So what we typically do is we take a sample, and the sample comes from the population. And if we did know what the population characteristics were, or the parameters, we could use probability, which can be thought of as the study of uncertainty, to make statements about how likely the sample is that we observe. And so we've got statistics, which are the characteristics of the sample. Those are things like x bar, s, p, and so forth. So we want to use these things to make statements about the parameters. And so by making assumptions about the parameters over here, we can use probability to make statements about how likely the statistics are, and that then allows us to do what we call statistical inference, or inferential statistics, to make statements about how likely these observations are. So in this chapter we're going to look at these sample characteristics, things like x bar, which is the sample mean, the sample standard deviation, and proportion, and so forth. And that's going to allow us to set up the discussion of probability that we'll do in Chapter 5 next week. So these statistics are the ones that we're going to talk about in Chapter 4 are actually called descriptive statistics, and that's juxtaposed to inferential statistics. And a descriptive statistic is just something that can be thought of and characterized using these different ideas here, and that's what we have in Chapter 4. So we have a numerical description, we've got measures of center, we've got measures of variability, standardized data, percentiles, quartiles, box plots, etc., correlation and covariance, group data, and skewness and kurtosis. So here are the learning objectives for Chapter 4, and let's go ahead and jump right in with numerical descriptions. When we want to describe a data set like what we did in Chapter 3, we use charts and tables and graphs. In this chapter we're going to talk about how to make a description of the data using numbers instead of charts and tables and graphs. Now the charts and tables and graphs that we did in Chapter 3 are actually types of descriptive statistics, but we're going to focus more on the measures of center and variability and shape, and these all come in the form of numbers or specific statistics that we will look at as we go through this. So the first measures that we're going to talk about are measures of center, and this is what we call the first moment. And there are two different versions of this. There's what we call a population mean and a sample mean, and just like we showed just a minute ago, The characteristics of the population are the parameters. That would be mu on the left here, and the sample characteristic is x bar. And notice that the formulas are very similar, except for what's the difference? The capital N is used in the population mean mu, and the lowercase n, which signifies a sample from a population, is used in x bar. So capital N is the population mean size, and small n is the size of the sample. If we're going to use Excel to calculate an average, we just use the function average and then put the data in, and we'll see some examples of that a little bit later on. One thing you should notice about this mean, this measure of center, the mean, is that every single observation has the same weight. So this summation here means that we're going to say x bar is equal to x1 plus x2 plus xn, all of that divided by n. So this is the same thing as what we have here. So every single observation that we take has an equal weight when it comes to determining this mean, which means that we could have some potentially very large values of x in the positive or in the negative direction that unduly influence the sample mean. And so for that reason, we have weird things like the starting salary of University of North Carolina geography majors being in the neighborhood of around $250,000. Now, you might think that sounds kind of odd, and it is a little bit. UNC geography starting salary equals $250,000. How could that be? If we're talking about geography, we're doing things like state capitals, rivers, lakes, streams, mountain ranges, that sort of thing. So how could the starting salary be $250,000? Well, it turns out that there was one UNC geography major that had a starting salary of around, by the time they graduated, of around $60 million a year, and everybody else had starting salaries in the $30, $40, $50,000 range. And so you might say, well, who was that one person? Well, his name was Michael Jordan, and he majored in geography. He left after his third year, so he didn't graduate until a few years later, and by that time he was an NBA superstar and had all sorts of income that is not typical of a geography major. So that brings up the point that maybe, just maybe, sometimes the mean isn't the best measure of center to use, although oftentimes, most of the time, it is going to be the best thing that we're going to use. In this situation, however, when we have an outlier, it's better to use the median. And the median is what's called the 50th percentile, or the midpoint of the sorted data. In other words, half the data is smaller and half the data is bigger than the median. If the sample size n is odd, then the median is the value right in the middle. If it's even, then it's going to be the average of the two middle observations. So if we do have an extreme value, it's way out there, Michael Jordan's salary, for example, that doesn't get the same opportunity to pull the measure of center up as it did with the mean. So you could have as big a maximum value as big as you like, and that's not going to change the median. Another measure of center is something called the mode, and that's the value that occurs most frequently. And we talked about modal classes in the last chapter, and this is the same notion. And this measure is usually only valuable if we're talking about categorical data or discrete data. So what's the relationship between the mean, median, and the mode? Well, it depends on the skewness of the distribution. If we have a symmetric distribution, as we have here, then the mean is going to be equal to the median, is going to be equal to the mode. If we have left skewed data, that means we've got some point down here that's really big, that's pulling the mean down, but the median is unaffected. And if we have right skewed data, in the case of UNC geography majors, for example, Michael Jordan's salary would have been out here at $60 million. Everybody else would be down here at around $30 or $40 million. So the mean gets pulled up, and the median is not affected by those extreme values. There are other notions of means. Geometric mean, for example, instead of taking the summation and dividing by the sample size, the geometric mean says let's take the product of all the observations and take the nth root of that. And this is something that's useful for calculating the average return over a certain number of years, let's say on a stock return. And then we've got growth rates, which are also a variation on that. Now, we're not going to do too much in this class with geometric mean and growth rates. In fact, this is the extent to which we are going to talk about these things. So at least you can say you've seen reference to geometric means and growth rates, but don't worry too much about making calculations and those sorts of things with these, unless it shows up on the homework. Another measure of center is called the mid-range, where we take the average of the maximum, the maximum and the minimum values of x, and it's a fairly simple calculation to compute. Not one that's used that often, to be honest, so we're not going to deal with it much at all. Another measure of center is something called the trimmed mean, where you remove the highest and lowest k% of the observations. And here's an example where we want to take a 5% trim mean. We've got 33 observations for the price to earnings ratio. So that means we're going to drop off 1.65 observations. We can't do 0.65 of an observation, so we're going to round that up to 2 observations. So the top 2 and the bottom 2 are going to be thrown out, and we're going to take the mean based on everything else. Here's a list of the functions in Excel you can use to calculate all of these things: average, median, mode dot single, geometric mean, min, max, divided by 2, and trim mean. Those are all things that we can use, and you'll become familiar with not all of these, but some of these things as we move on through the class. The next measure that we want to look at is that of variability. How much spread is there in the data is the question. And there are several different measures to use this. The first one is the range, and you just take the maximum value of x minus the minimum value of x, and in Excel it's just max minus min. It's easy to calculate, but it's like the mean is sensitive to extreme values. We have the sample variance, which is s squared is equal to summation of xi minus x bar quantity squared divided by n minus 1. So this is basically saying how far on average is each of the data points from the mean. And if we don't square this, then the summation turns out to be 0, so we've got to square that before we take the summation and divide by n minus 1. The reason that we divide by n minus 1 instead of n is because this x bar right here is estimating, it's an estimate for mu. And so because we've estimated mu with x bar, we've lost what's called a degree of freedom. So if that doesn't make any sense to you, don't worry too much about it. Just remember that we're dividing by n minus 1 instead of dividing by n. And the variance var.s is the sample variance in Excel. So there is a population version of this where you do know what x bar is, and so you would divide by n, not x bar, you do know what mu is, so you divide by n instead of n minus 1. Because if you know what mu is, then you can calculate that, although we in practice don't ever know what mu is. So other measures of variability that we're interested in that work for us that were very useful for us are the standard deviation, which just turns out to be the square root of the variance, So we get stdev.s that says the sample standard deviation. There's a population version of this as well. This is nice because it has the same units as the raw data. So if x is in dollars, s is in dollars, whereas if we were looking at the sample variance, if x is in dollars, the variance is in dollars squared. The coefficient of variation is just the sample standard deviation divided by x bar, the sample mean. Multiply that by 100. There's no built-in function to get that in Excel, although it's very easy to calculate still. And what this does is measures the relative variation in percent, so we can compare data sets. So if you're going to use two different data sets, you want to say how big is the variation divided by the mean. We can do that using this coefficient of variation. And the last measure of variability we're going to talk about is the mean absolute deviation. So instead of taking the square, here we're going to take xi minus x bar and take the absolute value of that and divide it by n. And with Excel you can use average deviation of data. And so the population variance is really what we're going to be interested in often, and here's the formula for that. Notice it's similar to s squared, but we've got a mu instead of an x bar and an n instead of an n minus 1. And if we take the square root of that, then we get the population standard deviation. So these two are going to be, or this one rather, is going to be the one that we end up using quite a bit in this course. The coefficient of variation is useful for comparing variables measured in different units or with different means. That's because standard deviation divided by x bar has no units. The units from the s get canceled out by the units from x bar. And so we have a unit-free measure of the dispersion, and this is expressed as a percentage of the mean. This tends to only work for non-negative data, so if we have a negative x bar or a 0 x bar, then that is problematic. Mean absolute deviation is one that we see quite often, and it's just the average of xi minus x bar, absolute value of that. So it's intuitive. We're just saying how far is xi from x bar in an absolute distance, and we're just going to take the average of that. If we compare these two different measures of central tendency and dispersion, we can see that sometimes we can have the mean correct, as in this case. So the desired distribution for a process performed by machine A, looks like we're drilling holes, is to have a mean of 5 something centimeters or millimeters or whatever it is. And we can look at the actual data and see that, yeah, we got the mean right, but the variation is bigger than it should be. So that's something, if we were working on this machine, would be a flag to us. Another way this can happen is we can have the variance correct. Notice this red distribution matches pretty well to the blue distribution, but the mean is off, so the holes being drilled are a little bit smaller than they should be. You look at these small numbers and say, oh, that's close enough, but in actuality that's not necessarily going to be close enough, so we're going to have to talk about what this means in terms of statistical models, and we will do that a little bit later in the course. So we're going to stop this video at this point and make another one, so come back and check out the next video where we continue with our discussion of Chapter 4.